should. She'll get it. I know she will. Alright. So, center of mass versus center of gravity. As long as the gravitational field is evenly distributed, so you're about the same distance away from the center radius, then they're basically the same thing. When you get into very massive objects, such as the moon, even then, the moon's very far apart compared to Earth. But if you were to get like a ladder the length of one radii, then obviously there's less gravity at the top of the ladder than on the surface of the Earth. So center of gravity would only change in very rare scenarios like that. If you're on the surface and you're dealing with ordinary objects that are less than several thousand kilometers in size, center of gravity and center of mass are the same thing. And for the most part, we'll be treating those two as that same because there's almost never a scenario where it's different. If you want to find the center of gravity of something, you can balance it on one point and it'll all try to equally distribute itself. And if you put a string like it's showing on this, that string will pass through the center of gravity. If you do it from multiple different points, they should all intersect at one point. And then if you were to bounce it, you can bounce it on the tip of your finger at that point. You've probably seen this. Have you seen that? So this, the wings are actually very heavy and far away. And what happened is they designed this shape so that the center of gravity is at this one point, which means it can perfectly balance at one point. So what determines whether or not something is balanced? The location of the center of gravity is important for stability. So the Leaning Tower at Pisa, why doesn't it fall over? If you draw a line straight down from the center of gravity, and if that line falls inside the base of the object, it will experience stable equilibrium, meaning that it will balance. If it falls outside the base, it will fall over. Out of curiosity, so let's look at there are something called chaotic or unstable equilibriums. So if it falls outside the base, it is not an equilibrium. It will continue going over. But if it falls inside the base, it's technically an equilibrium. Most of the time it'll be stable, but there are few situations where it's unstable. What unstable equilibrium would be is imagine a pencil with a very sharp point. Now, any amount of movement, such as an air molecule coming over and bumping it, will cause that center line to fall away from that point. My question is, how long? Imagine when you have a perfect pencil. A mathematically perfect, obviously this can't exist in real life. But imagine that this is a perfect point, like less than an atom. Imagine we have an infinite shape. And then imagine we bounce it like this, and one air molecule comes over and hits it. So, not very much, but because this is infinitely a single point, how long do you think it would take for this pencil to fall over after being nudged by a single atom? A little over 3 seconds.
Balancing a pencil or any other top-heavy object on its tip is quite a precarious task.
It's easy to see why top-heavy objects are unstable. They just want to fall down.
Any little nudge will put it off balance, with gravity happy to pull its center of mass even more off balance.
Our Earth is like a treasure.
Balancing a pencil or any other top-heavy object on its tip is quite a precarious task.
It's easy to see why top-heavy objects are unstable. They just want to fall down.
Any little nudge will put it off balance, with gravity happy to pull its center of mass even more off balance.
So the two forces is the gravitational force or its weight and the normal force. And because this can only balance, and in real life the area is touching is not a single point. But if you think of it theoretically, it would be a single point. So there's only one for very precise position for it to balance theoretically.
And the more off balance it is, the more gravity pulls until... Physicists call this kind of tipping an inverted pendulum, because it's kind of like an upside-down pendulum, and careful mathematical analysis of inverted pendulums will tell you the obvious. They're really unstable. In fact, these equations predict that if a perfectly balanced pencil with a perfectly sharp tip were to get nudged off balance by just 1/10,000th the width of an atom, it would take only 3 seconds to fall over.
3.1 seconds. So this was off balance by 0.0001 width of an atom, it would fall in 3.1 seconds. So initially it's going almost 0 meters per second. But this is exponential, and humans really can't think of exponential growth. Even though that 0 is very, very slow to begin with, in about 2.6 seconds, you start noticing it fall. And as soon as it starts noticing it fall, it immediately finishes falling.
There are indeed acrobats who can balance poles with other acrobats on top, and robots that can balance and catch and throw upright sticks, and people who make seemingly impossible artistic rock stacks. But in all these cases, keeping the objects balanced either requires an active stabilization effort, or else carefully taking advantage of the fact that the balancing point isn't actually a point. So the question is this: can you balance a pencil sharpened to a perfect single atom wide tip on its tip without active stabilization? Well, to start, you'd better get rid of all the air bumping off the sides of the pencil, since the kinetic energy of a typical oxygen molecule is enough to destabilize the pencil. Remember, if the pencil gets off-center by even 1/10,000th the width of an atom, it'll fall down in under 3 seconds. And you'd better cool the pencil and table down as close to absolute zero as you can, since the thermal jiggling of their atoms when they're hotter will similarly jiggle the pencil off balance. But even then, matter at very small scales has a spread-out wave-like nature, which means you can't have both the pencil perfectly upright and not moving at the same time. And while this quantum effect is never a real-life inhibitor of precarious pencil balancing, it means you never even could succeed. However, it's still fun to see how long you can keep a pencil balanced on your fingertip. The shorter the pencil, the harder it is. My best time for a standard 19cm pencil was 1.3 seconds. Think you can beat it?
This Minute Physics video was brought to you by Audible.
So in real life, you couldn't even balance a perfectly pencil because everything is in constant motion. But if you were to try to build something, and you're like a column or something, and you wanted to check whether or not it will stay balanced or if you're worried about something tipping over, it's also why you stack the largest blocks at the very bottom, because you take the center of mass of whatever structure you have, and as long as it remains in the space, it won't increase the size of the space, then any small deviation will still keep it in space. So let's look at centripetal force. So recall acceleration. What is acceleration? The speed, change in speed and direction. So acceleration is change in velocity over time. Velocity is speed plus the direction. So you accelerate if your speed is changing or if your direction is changing. So if you are moving at constant speed, but your direction is constantly changing to keep you going in a circle, you must be accelerating. That means, and anything with mass and acceleration, there's a corresponding force because F equals ma. So any force directed toward a fixed center is called a centripetal force. Centripetal force means center seeking. That's what the centra means. Or toward the center. To whirl a tin can at the end of a string, you pull the string toward the center and exert a centripetal force to keep the can moving. So, in order for that can to continue moving in a circle, the string is pulling it toward the center. The reason why you're able to orbit around Earth is Earth's gravity is pulling it toward the center of the Earth. So, and if you were to let go of it, so if you were to let go of the string, that means that it no longer has a force or acceleration, and it will continue moving in a straight line, and without changing any direction or anything with the same velocity. Centripetal force depends upon the mass of the object, the tangential speed of the object, and the radius of the circle it's following. So centripetal force is equal to mass times tangential speed squared divided by radius. When a car rounds a curve, the centripetal force prevents it from skidding off the road. If the road is wet, or if the car is going too fast, the centripetal force is insufficient to prevent skidding off the road. So the chances of you actually sliding and failing to make a curve basically depends on the only force whenever you make a turn to the left is friction. So if the friction force isn't strong enough to keep you turning, your car is going to continue going straight. Suppose you double the speed at which you round the bend in the curve, but what factor must the centripetal force change to prevent you from skidding? So the equation is mass times tangential speed, this is your linear speed, squared divided by radius. So if you double the tangential speed, how much would the force change? So you're putting a 2 here, so 1 times 2 squared. And on the test corrections, you even make this mistake. So I said replace all the variables with 1, but you would leave squares in there. So 1 times 2 squared divided by 1 is 4. It would quadruple because your speed is doubling, but the speed is squared. So a double squared is 4 times. So if you double your speed going around the corner, in order to maintain the rotation or turn, the force has a quadruple, which is why so it's quadratic, which is why going around the curve too fast, the faster you go, the force is double or quadratic in the form of it, not linear. Suppose you take a sharper turn than before and half the radius. By what factor will the centrifugal force need to change to prevent skidding? Yes, it would double. So 1 times 1 squared is just 1. 1 divided by half is 2. We often like thinking about centrifugal forces. Fugal, I think, means fake. Let me look up my Greek prefixes. Fugal. No, fugal means fleeing. So it is. So, centrifugal means center fleeing or away from center. This is a fake force. It depends on your frame of reference. Usually all good frames of reference are non-rotating. So, for example, the frame of reference on Earth, we see the sun rotating around the Earth. Because we're in a rotating frame of reference, or view of the universe outside our reference point is kind of wrong. We know that if we were to stop rotating, stop spinning around Earth, and look, we would see the Earth orbiting around the sun, and not the sun orbiting around the Earth. Centrifugal force is a force that you would experience if you're inside a rotating object. It's only there because you're inside the rotating frame of reference. It's not real, but its effects are real. So like for example, let's say you're driving a car. Or let's imagine a tin can being done on a string. And it's going around in a circle. And in order for this can to continue going around in a circle, there has to be a force, the centripetal force, or centripetal force, pulling it in this direction, right? So this is the only force acting on the can, or car if you're going around the corner. Now imagine you're sitting in the can, or sitting in the car going around the corner. What would it feel like to you if you suddenly make a left-hand turn? You would feel a force to the right. This is the, I always forget how to spell it, centrifugal force. Now, if I were to animate this, what really is happening is, so the can or car is making a straight line path, or making a circular path. And if we draw, if you aren't physically attached to the car, what happens is, Newton's first law of motion. An object in motion tends to stay in motion, moving at a constant speed and direction. You would tend to move in a straight line. But if you look at where you were compared to where you are now, again, you're referencing the object you're in. You're referencing the car or can. It appears as if you were pushed outward, when in actuality, all you were moving in a straight line. It is a common misconception that a centrifugal force pulls outward. Again, this is incorrect. If the string breaks, the object doesn't move radially outward. Instead, all it does is continue moving in a straight line. Because no force is acting on it. This is Newton's first law. However, if your reference frame is the car, you're measuring everything in reference to inside the car, the force would feel as if it's moving or fleeing outward in a circle, radially outward. But what's happening is you're moving in a straight line. This can be used to create artificial gravity. So the central force in a rotating reference frame is a force in its own right. So even though it's I have to put in quotes, a fake force, meaning that if you were to change your reference frame to where it's not rotating anymore, it disappears. But at the same time, it's as real as any other force. So it's both fake and real at the same time. So if you were to put a bug inside of a can and spin it, the centrifugal force will push outward and keep the bug on the bottom of it. So this can be used to simulate gravity in space. By spinning a space station, occupants will experience a centrifugal force inside, similar to what the bug can feel in the can. So if you were to get a large enough disk and spin it, you could simulate 9.8 meters per second squared. Again, if you're an outside observer looking in, what's happening is you're trying to you're trying to, so there's a force, so you're trying to move straight, and which causes, remember, normal forces act perpendicular. So you would be pushing perpendicular to the surface, which would then push back. And so, because the force is going to be perpendicular to what surface you're on, it's going to feel as if it's radially outward. So to simulate an acceleration due to gravity, g, which they use 10, that should be 9.8. So an example of achieving this is if you had a radius of 1 kilometer and a revolution of 1 revolution per minute, you would get 10 meters per second squared, roughly. So, what's odd about this class, I really need to change it up, is how Texas Resources say I should teach this class, is I should teach energy, rotation, linear motion first, and then momentum later. But momentum is a very good concept. We're going to have a whole section on just momentum later. What you should know, and for now though, is momentum is equal to mass times velocity. Momentum uses the letter P, M times V. Another thing is momentum is conserved. Just in the same sense as energy. So energy can't be created or destroyed. Momentum can't be created or destroyed. So, for example, if you have a ball of mass m and it has a velocity of v, and it were to strike an object of mass 2m and stick together, So the total momentum here is mv. This has a momentum of 0 because it's not moving. Afterward, if they were to stick together and become 3m, then the momentum of this system would have to be mv. So the velocity would be a third. So you get 3m for the total mass of them combined, times velocity over 3. 3's cancel out, giving you mass times velocity, because momentum is conserved. We also have angular momentum. Angular momentum is also conserved as rotational momentum. The inertia of rotation of rotating objects is called angular momentum. This is analysis to inertia of motion, which is momentum. So at this point, I'll go ahead and state every equation for linear, I should say almost every equation for linear, can be converted into rotational. So let's look at displacement. Our distance. For linear, it's just x, measured in meters. For rotational, it's theta, measured in radians. So this is your angle. For speed, or velocity, it's going to be v, which is in meters per second. And for rotational, it's omega, and it's in radians per second. For acceleration, linear acceleration is just a, and it's in meters per second squared. It's alpha. This is rotational acceleration, and it's in radians per second squared. We have force. Force is F. It's in newtons. And in rotational force is torque, which is Newton times meter. Technically, there's a radian in here too, but radian is considered a unitless unit. It's an imaginary unit. A radian can be thought of as a meter divided by a meter, which cancels each other out. There's another one. I'll think of it in a little bit. Oh, inertia. What is linear inertia? Mass, which is kilograms. And rotational inertia is moment of inertia. It's also called moment of inertia. And its units are kilogram times meter squared, because rotational inertia depends on the distribution of mass. And so let's look at formulas. So looking at formulas. Force equals mass times acceleration. what would be the equivalent rotational formula? Alpha. Should be making it more like that. So this is another equation for torque. We can have, for example, let me look up, make sure. Rotational. We can have momentum. So momentum is equal to mass times velocity. In which case, for here, we have angular momentum. So this is angular momentum. And it would be equal to I times omega. So we have the equation x equals v naught times t plus 1/2 at squared, your kinetic equations. In rotational mechanics, that would be theta equal to omega naught times t plus 1/2 alpha t squared. So how much you've rotated, the angle you rotated, times your initial rotational velocity, same thing. You can have, for example, the distance you travel is equal to your average, so average velocity, times time. This could be theta equals your average rotational times time. So if it's constant, then it's not average anymore. Oh, and technically I'm wrong. It shouldn't be displacement, it should be position. The current position you're at. Displacement is delta x, change in position. That's what I'm looking for. So there's a connection between them. So you can basically straight up convert between them, but there is a few formulas to relate them. So we have tangential speed, so this is your linear speed, is equal to your distance from center of rotation times your omega, your rotational speed. So rotational speed times the radius is equal to tangential speed. Your change in, or your displacement would be equal to r delta theta, which makes sense. So here is why radians is useful. So if you have a circle, and let's say that we move some theta, and this has a distance of r. If theta is in radians, then this distance right here, the length on the circumference, is equal to r times theta. So if you're in radians, then you can directly convert distances between linear and rotational. So how much this angle changed? So this is your change in angle. It should probably be delta theta to give you a better idea. So if you're at 0 radians and you go to 1 radian, you travel a distance equal to r. Because 1 minus 0. And we can also get acceleration. Linear acceleration is equal to r times rotational acceleration. Because how much this and also if a ball is spinning on the ground, so if this goes one revolution, so if it spins and rolls 1 revolution, it's traveled the same distance as the circumference, right? So if you were to roll it 1 full rotation, it's traveled the full circumference. So basically, you can convert just by multiplying r into it. Because radians gives you the distance on the circumference. So, angular momentum represented with L, which is weird. Do not get confused with linear momentum. Linear momentum uses a P. So angular momentum is rotational inertia times angular velocity, or rotational velocity. For an object that is small compared to the radial distance to its axis, magnitude of angular momentum is equal to mass times tangential speed times radius. So momentum is mass times velocity. Angular momentum is I times omega. So mass is I, speed is omega. We know that mass or inertia. The common equation for inertia is mass times radius squared. And if you remember this equation, that tangential speed is equal to r times, I'm sure I got that right. Yeah, r times omega. What we can do is solve for omega. So omega is equal to dt, I should use capital R, over r. And we can plug that in here. Tangential speed over r. Well, this r is going to cancel out with a square here. And we're left with mass r dt. And usually they rearrange it like this, times r. And this is equal to your angular momentum. Which makes it very nice Because this is basically L is equal to R times your linear momentum, which matches up with these equations. L equals R times your linear momentum. So, whirling a ball at the end of a long string, planet goes around the sun, they have some momentum. We get the equivalent law of momentum. So, law of momentum states that it's conserved. External net torque is required to change angular momentum of an object. So this is a rotational version of Newton's first law. An object, our system of objects will maintain its angular momentum unless acted upon by external net torque. You could also redefine Newton's first law in terms of momentum. An object's momentum doesn't change unless an external force is acted on it. Suppose you are swirling a can around and suddenly decide to pull the rope in halfway. By what factor would the speed change? And speed in this case is tangent speed. So remember that angular momentum can be written as mass times tangential speed times radius. So if you decrease the radius by half, the tangential speed will double. So angular momentum is always conserved too, just like linear momentum.
Of an isolated system will not change if there's no, well, since it's isolated, so there's no external torques acting on the system. In the horizontal plane, then, if I set myself in rotation, then in principle I get a certain amount of angular momentum. And aside from the small amount of friction that would exist in the bearings, then in principle my rotation rate shouldn't change. All right. Now, angular momentum is a combination of both the moment of inertia and the rotational rate. And so if I can change my moment of inertia, which I can by changing the mass distribution with respect to the axis of rotation.
So because angular momentum is always conserved, if you change your inertia is distribution of mass times mass, or equivalently, if you change how the mass is distributed, if you increase the distance mass is, your momentum can't change, which means your speed must change to compensate.
Then by changing that moment of inertia, I can also subsequently change the rotation rate. So if my moment of inertia is high,
So he's spinning, and what would happen if he brings the balls in closer to him? A lot faster. This is why a ballerina, when she's spinning and she puts her hands out, she generates some angular momentum, and then she can increase the rate in which she spins by bringing her arms inward and closer to her body. Or I'm thinking more of an ice skater, but Still the same principle. We're really out of time. I wanted to go over one last topic though. And remember, these are all vectors. What do vectors have? Direction. So when you have a velocity, it'll be your speed. Technically a vector. Put arrow over it. That or either or. It has a certain direction. So if I were to take, and let's imagine a disk spinning like this, what happens is, so if it's spinning around and trying to, so this is a perfect circle. If you were to, this is the right hand rule, if you were to wrap your fingers in the same direction, curl your fingers, your thumb would point in the direction of the vector. So if this was rotating like this, so the direction would be pointing down into the paper. If it's rotating like this, curling in the same direction of rotation, it'd be going up toward the camera, out of the paper. This is technically not a real vector. It's called a pseudo-vector. The reason why it's not a real vector is because it depends on reference frame. A true vector, no matter how you look at it, always points in the same direction. A pseudo-vector changes based on how you're looking at it. But we'll continue tomorrow.